So we have the volume of revolution, right? So we have two methods, disk method or shell. No, that's not the shell method. Washer, right? The washer, depending on so the idea was if you rotate around the x, then the integral is a dx integral. Okay? So if you rotate around the x, then the volume is pi, the integral from a to b, the function squared dx. Or if it's the region bounded by two curves, we had the volume was pi, integral from a to b, the difference of squares of two functions. Dx. Yeah, so if there's a hole in the middle. Now if you rotate around the y, you'll get a dy integral. So you have very similar formulas. Volume is pi integral from c to d, some other function. Well, let's call it g of y dy. Or if there is a hole in the middle, if it's bounded by two curves, it's pi integral from c to d. I'll just call them f and g. Is that okay? F of y and g of y. Dy. So that was the disk slash washer method. So I think that's section 7.2 maybe? Good? Okay. Then, that was the one I know I called it two. Now, the second method we discovered at the end of Friday was the method of cylindrical shells. So the formula there was if we rotate around the x again in the same column, we'll actually get a dy integral. And the integral was v equals 2 pi, an integral from a to b, x times f of x. I'm sorry, y times f of y dy. If we rotate around the x. Now rotate around the y. We'll get a dx integral. So v equals the integral 2 pi from c to d x g of x dx, or whatever your function is. Okay? So two formulas. Sometimes one works better than the other. It depends which way you slice it. Sometimes they both work fine. I just want to do an example where we can use both of them. So let's say, let's rotate region bounded by let's do y equals x and y equals square root of x, and let's rotate around the x. So if we rotate this thing around the x, we'll get, I don't know what it is, but this type of a thingy. Is that okay? So we can do it both ways. Let's do it the shell method. No, not the shell method. What do we call it? The washer method. Let's do the washer method first. So that's when we slice it along the axis of revolution. So then the volume is pi integral. So the x will range from 0 to 1. And then it will be the upper function squared minus the lower function squared, right? So the upper function in this case is the square root. So it's a square root of x squared minus the lower function, right? Which would be just x squared dx. Is that okay? So that's a difference in radii, difference of squares of radii. So we end up with the integral from 0 to 1. And then just x minus x squared dx. Good. Now that's a friendly integral. So we get pi is x squared over 2 minus x cubed over 3, evaluated from 0 to 1. Plugging 0 gives you 0, so the only thing that matters is 1. So we get pi times a half minus a third, right? And what is a half minus a third? 1/6. So it's pi over 6 then. Is that okay? It's a very friendly example.
So do we just have to kind of think about it abstractly in our mind brains and then determine which method we're going to be using to...
Precisely. I just want to make sure that gets on the recording. So what Aaron is suggesting, that we'll have to think about this in our mind brains and then decide which method to use. It's irrelevant in this case. I'm about to do the other method, and we should arrive to the same answer. But then we'll do a couple exercises. We will see one is better than the other. But yes, definitely use your mind brains. I like that. Okay, so that was the washer method because we were slicing it like that, right? So we were getting little washers, right? So we were just adding them up. Okay. Now, the shell method, and again, like if we really break down the formula for the shell method, what this formula tells us, because if we understand the formula, we will be able to use it pretty well. This is the height of the shell, the value of the function, right? This is the radius of the shell. So when you start revolving that little strip around the y-axis or the x-axis, there's a certain radius, and the radius equals precisely whatever the y or the x value is, how far away the strip is from the origin, so that's whatever the x value is, right, or the y value. So, so that's the radius. So if you understand that it's a radius times the height, and 2 pi is 2 pi, that gives you the circumference. So 2 pi r is the circumference. And, dy is the thickness of each shell, but we don't need to get that deep. If we just understand that this is the height and this is the radius, we'll be able to set up those integrals without needing new formulas, because technically this is the region bounded by two curves. We haven't done it with the shells yet. We haven't derived that formula. But again, if we understand the height times the radius, we should be okay, right? So if I draw the shell will look like this. We're slicing along the y-axis, and we'll rotate that strip around the x-axis, right? So, what do we get? We get another one of these. Is my picture getting a little busy? But basically, this is what I end up with. I end up with something like that, right? So basically, we're just adding a whole bunch of these shells, and eventually it's going to fill in the volume that we created. So the radius of this shell is just, whatever the y value is, right? You're slicing along the different y values. So the radius is the y, but the height in this case, well, what is the height in this case? How do you figure out the height of which one of those? So basically the length of which strip. If I look at it this way, what do you think? Yeah, so it's the difference of the right function and the left function, right? So it's x minus the square root, right? If I just look at it like that, figure that. So this would be the x minus the root x. So just like before, we'll take the difference. So then if I set this integral up using the shell method, luckily, y also ranges from 0 to 1 in this case. I mean, it doesn't have to be the same. So you have to pay attention that your limits of integration most likely going to be different. But we'll set up the volume. So there's going to be, again, 2 pi integral from 0 to 1, and then y times, well, the difference of these two functions. Now, what is the problem right now? Can I just write this expression in that integral? No, why not? In terms of y, so I need to convert them in terms of, so x equals y, and square root of x equals y, right? So therefore, what is x equals to from the second one? Y squared. The first one remains to be y, right? So it's just y minus y squared, right? So let's see where that's going to take us. Keep in mind, we kind of know the answer already. The answer should come out to be pi over 6. If it's not, then we're doing something wrong. I mean, it hasn't changed the shape. We're just integrating it differently. So then we have 2 pi integral from 0 to 1, y squared minus y cubed dy, right? Integrate 2 pi times y cubed minus 3, sorry, y cubed over 3 minus y to the 4th over 4 from 0 to 1. We plug in 0, we get 0. When we plug in 1, we'll get 2 pi times a third minus a fourth. And a third minus a fourth is 1/12. So we have 2 pi times 1/12, which is still pi over 6. So we still get the same answer. And again, it's always beneficial to draw those little pictures and really understand the formula, where the rotation comes from. So that will help you with the which functions subtract from which. Otherwise, you have to memorize too many formulas for each different case. If you really understand where those little strips come from and how you rotate them, then you just kind of do it. You just need to know the basic formulas, and then you'll do all the shapes. So having that in mind, or keeping that in mind, I want us to do a series of problems. We'll use our mind brains to. Yeah, I can certainly do that. To figure out which method is more appropriate. So yeah, so I think the disk method was in section 7.2. The shell method is in section 7.3. Is that right? I think it is. How's that? We good? All right, let's do this example. I want us to take a very friendly shape. So region bounded by y equals 1 over x equals 1, x equals 3, y equals 0. So 1, 3, so it's something like that, right? And the 0, so this is the region. So now I'm going to start flipping this region all over the place. So the first thing that I want to do is just to simply rotate around the x-axis. So the picture here, you have this little region, and we'll just rotate around the x-axis, so you're going to get a nice little setup like that, right? So again, we can do this problem both ways. One way is actually going to be a little harder than the other. One way we'll just set up one integral and we'll be done with it. The other way we'll have to get a little more creative. So which way do you think is the quickest or the easiest one? That's great. If I just slice it along the x-axis, I'll just get a bunch of little disks all together. If I do the shell method, see what will happen. So this will be the shell method, right? So when I cut along the y-axis, first I'm cutting between the curve and the line, and then I'm going to be switching and staying between line and the line. So technically I can still set it up, but I'll need two integrals. I'll first have to do the integral between the curve and the line, and then between two lines. Between two lines, I can just use simple geometry, just a cylinder. I don't have to add them. But if I just do the disk method, then I'll just set up one friendly integral and I'll be done with it. So then v equals pi, and then the integral, again, we're rotating around the x-axis, so it's going to be a dx integral. So it's from 1 to 3, and then it's simply whatever our function is squared dx. Okay? So whatever that equals to, you can do the integral. Let's just do the setup. We'll just do little setups, because I don't want to take time integrating. You can integrate this, right? What? I don't know. Okay. Let's rotate the same thing. And again, just setting up. I don't want to integrate. So rotate around the line y equals -2. So we'll rotate around that line. So we get a thing like that with a hole in the middle. Yeah. I don't know how far this is about. So again, we're going to do it as a, well, in this case, it's more of a washer method, but we'll still slice along the axis of revolution. Again, we're revolving against axis parallel to the x-axis. So we're going to be slicing along the x-axis. So we're going to have a dx integral, right? The only question is what we're going to integrate. And we can treat this as the, the area between, the region bounded by two curves. And then on Friday, I think, we were kind of flirting with this idea. When you start rotating around the alternative axis, then you can almost cheat a little bit. You can think of this as an x-axis, right? And then with respect to the line y equals -2, the curve 1 over x is really 2 units up. So this is 1 over x plus 2, right? So that's my, that's my upper curve. Right? So that's my outer radius, so I can write it as 1 over x plus 2 squared, right? Minus, well, this line, right? This is the other line, the original x-axis that bounds the region, but the original x-axis with respect to the new axis is 2 units up, right? So just y equals 2. So I can say it's minus 2 squared. So the other thing, dx. Okay? Now again, whatever that equals to, you open up the parentheses, you simplify, then you integrate, right? But at least we got the setup. So this is the, again, for some reason in my head, you get the same formulas as the book does, but this is new 1 over x plus 2. If you consider this as the new set of axes, if this is x, then this line becomes y equals 2, right? So you just kind of shift everything 2 units up. Is that okay? Questions on how we got that? Again, it's the outer squared minus the inner squared, the radii, and then, you just integrate that. I don't want to integrate. Yes, the limits will, in this case, will still be the same. Thank you. So since you're just looking at the region, we went from 1 to 3. So that's from 1 to 3, yes. Good. How about we'll rotate now around the y-axis? So I'll draw a picture. So again, here's that region, 1, 3, and we're going to rotate it around the y-axis. Okay? So we're rotating this around the y-axis. So slicing along the y-axis, as I mentioned before, will be a little problematic. You have several different shapes involved. So if I stick to slicing along the x-axis, then I'm going to think of this as a shell method, which is totally appropriate, right? I can set this up as a shell method. So I'm rotating this little cylindrical shell, so I'm just going to add them all together. And remember, when we do shell method around the y-axis, we slice along the x-axis, so we're going to end up with the dx integral still. But since it's a shell method, we'll get 2 pi, and remember again, dx integral. So then what are the limits of integration? Yeah, still from 1 to 3, that hasn't changed, right? Well, again, the radius of each shell is simply whatever the x is, right? As you integrate from 1 to 3, x will range from 1 to 3 will be the radius from 1 to 3. So that's still x times the height, and the height is 1 over x, right? X and x cancel, so we'll actually end up with a really nice integral, which is just dx from 1 to 3. X is canceled. How's that? Does that make sense? So again, I don't want to compute this. You can compute this. All right, let's rotate this thing around y equals 3. We're going to take the same region and flip it around the line y equals 3. And again, I just want to set up the integrals, because the integrals come out to be pretty simple.
We're going to talk about, like, rotating things or
No, let's not. We're not going to do that. We tried last year, and we kind of got weird. But you want to do the, we'll talk, yeah. You want to rotate the whole axis. That involves some, matrixy type of change of, so we're getting something like that, right? Now again, this, just the way this region was laid out, is just beneficiary to keep setting it up as a dx integral. Now in this case, so we're going to go for the washer method. And again, if we think about this line as a new x-axis, then what is this line? No, this is the x-axis now. 3, right? So this is y equals 3, so we just kind of change it, right? But you're right, it's 6 up from the original, but yeah. Now how about this graph? Only negative 1 over x plus 3, right? So it's a flipped 1 over x, so it's negative 1 over x, shifted 3 units up, right? So it has the asymptotic approach of 3. So here's the inner radius, here's the outer radius, right? And then we'll set up everything else in the same fashion. We'll do the volume equals pi, still the integral from 1 to 3. Now in this case, the outer radius of revolution is 3, minus the inner radius, which is the curve, and I can write it as 3 minus 1 over x, quantity squared, dx. Is that okay? This one? Mm-hmm. Well, here it is. I just rewrote it as 3 minus 1 over x. So here it is. Well, because again, I'm just thinking about, with respect to this line, y equals 3, so it approaches 3, so it's a flipped graph 3 units up. So basically algebraic, I'm just going backwards. Does that make sense? This is, for some reason, my head works well with this setup. When we're going to do the shells, we're just going to do it straight up. We're not going to try to think of shifting anything. We'll be able to figure out the shells. Because the shells, it doesn't matter what you rotate around, your height stays the same, because it's the height of the function. The only thing is going to be the radius of rotation. That's what we'll have to worry about. It's actually easier to think about the shell straight up. So let's do that. Let's rotate around x equals 5. Yeah, right. So we just, when you slice along the axis of revolution. Now, let's rotate around x equals 5. And you'll see we can do that. The shell method is a little easier when you're rotating around alternative axis. So then we'll get something like that. And again, it's really important that you sketch these things and you're really trying to understand what are those individual little pieces are, those little shells. Okay, because again, the way the formula works, you need to have the radius of rotation, that will be the radius, the distance from the axis of rotation to the actual little strip. Now the height, it doesn't matter what I'm rotating around. I can rotate around 5, I can rotate around -5. The height of each piece will be the same. The height will be defined by the function 1 over x, regardless where I'm rotating, if I'm rotating around the vertical axis, right? Do you agree with that? Doesn't matter what I'm rotating about. These pieces will have the same height. The only difference is going to be is the radius. This is going to change the volumes. So if we keep this in mind and we'll try to set this thing up, v equals 2 pi, and again, it's going to be the dx integral, because we're slicing along the x-axis, so the x will still vary from 1 to 3, right? From 1 to 3. And remember how it is. It is the radius of each shell times the height. So it's r times h, right? H is just given by the, whatever the function is. So h is given by the function 1 over x on the interval from 1 to 3. So it's just 1 over x. That's the height, right? Now the radius, actually we have to think about this. So we're rotating around the axis given by x equals 5, right? Well, what is the largest radius going to be when I'm actually taking this piece right here, and I'm rotating it around the x equals 5? What is the radius of this rotation? 4, right? This radius is 4. What is the smallest radius? 2. How are you getting that? 5 minus whatever the x value is. So this is going to be the radius. In this case, the radius is 5 minus whatever the x is as you're traveling from, as x goes from 1 to 3, right? X goes from 1 to 3. The radius changes from 4 to 2, so it's 5 minus x. So if you just kind of think about this for a minute, then you're going to get that radius. And it's going to be easy. You don't have to memorize anything extra. As long as you understand it's radius times the height, and we'll just figure out what the radius is. Fun? Whatever that equals to. Whew, yeah. What do you think? Does that make sense? All right, good. So that's your section 7.3. Any questions? Yeah. Well, you're just kind of looking at, depending on which axis you're rotating around, right? So we did the very first example. Yeah, this one, because we did the same region both ways. And then actually in this case, it didn't change either. So that's a bad example because it was a 0.11. But let's say, hypothetically speaking, this was 0.12, whatever, right? So in this region, we could have done both ways. So that's just depending on how you do that. If you slice it along the x-axis, you're just going to observe, well, what is the range from the x-axis? So in this case, it was from 0 to 1. But we can also do this problem using the shells. Doesn't matter in this case. So if you do the shells and you rotate around the x-axis, you're going to end up with the dy integral, right? So this is where you're going to look. Okay, it's a dy integral. Well, what's going on the y-axis? What does it range from? From what to what? So in this case, I mean, if I change that, it'll range from 0 to 2. Okay, so then you just kind of have to look at, depending on which integral you do, dx or dy, and then you look at how your x or y changes for that region. That's about it. Now, I know both examples were the same, but it's just depending on how you look at it. Is that all right? Okay. So let's do the arc length. So that's section 7.4. So the arc length. So the arc length, it's literally, if I have a function, I have a graph of a function that does whatever between A and B. I literally want to figure out the length of the curve. So, it's like if I put a little string over the graph, then I pick it up and I stretch it and I measure the length. So literally the length of the curve, that's what we're trying to find out. It's not the area under the curve, not like that. We're just doing a one-dimensional measure. We're just trying to get the length of this thing. Okay? So we can apply our calculusy approach to life. When we get things that are curvy, that are hard to measure, we're going to turn them into things that are not curvy, that are easy to measure, right? So how would we approximate a curvy line, the length of a curvy line? Yeah, just would approximate the little straight line segments, right? We're just basically going to do, a little segment here and a little segment there. I'm trying to really kind of fit the curve. I'm not doing the tangent lines. I'm meaning to overlap the curve. So, we're going to be taking 2 points, x sub I and x sub I plus 1, and then we're going to take this little line segment, and we're going to find the distance between those 2 points, right? Because we have a distance formula that will allow me to find the length of the straight line segment, right? The distance formula, what is the distance formula? It's a square root of, okay, so this is how you were taught in whatever algebra, so it's that, right? Now, we're not in algebra, we're in calculus. We can get, again, in 2 and 1, this is your I and I plus 1, right? In more general terms, because you have more than just 2 points. But to avoid, and I'm really going to give you a shortcut. I mean, we can get into really, really heavy derivation of this formula that might involve a mean value theorem at some point, because those are the best proofs. But we can, we'll do a little mathematical hand waving in this one. Is there an alternative way of calling difference in x's? Delta x, right? And this is delta y. So really, the difference is just delta x squared plus delta y squared, right? So it's a square of the differences and a sum of that. Sum of squares of differences under the square root. This is just pure algebra. There's nothing fancy. It's a Pythagorean theorem. That's all it is. Now, if I do a little mathemagic here, I can do some creative factoring. I can factor out the delta x squared to get 1 plus delta y squared over delta x squared with the delta x squared on the outside. So I'm just kind of factoring delta x squared. And the way you factor, you just divide both terms by whatever you're factoring, so delta x squared becomes 1, and you get a denominator of delta x squared, right? And of course, now it's a multiple of delta x squared, so I can take the square root of the square. So I'll end up with a square root of 1 plus delta y over delta x. I can write it as quantity squared with a delta x outside the radical. This is my algebraic way of just kind of putting the delta x on the outside. There's another way to prove that. I don't know if I want to. It'll get all messy. We're definitely going to use the mean value theorem at some point. And we'll have to fake the setup for the mean value theorem. They'll go, oh, mean value theorem, derivative. But so anyway, so this is nice, right? So therefore, the total length, you'll just add them all together. You'll just add, from 1 to n, and you're adding those, let's call it some di. So you're adding all those little expressions. So we get the square root of 1 plus delta y delta x squared with the delta x on the outside. But if you take the limit, as n goes to infinity, your partitions get smaller, those line segments get smaller, sigma becomes the integral. So the arc length, and usually we use capital S for that, will be given by the integral from a to b over square root of 1 plus dy dx squared dx. So basically, it's a 1 plus the derivative squared. That's what it says, right? It's 1 plus the derivative of the function squared under the square root. It's not calibrated very well. It's hard for me to write it. But can you read that, what it says? Or I can always say it like that. So the arc length is the integral from a to b, and then it's a square root of 1 plus the derivative of x. I mean, derivative of your function squared dx. So either dy dx squared or f prime squared. Okay? Now, these problems are, it's like as much as algebraic fun you can have. It's these problems. Because you get a square root, in order for this to work well, you kind of want to get a perfect square under the square root. So I cannot just pull a function out of my head and just like do the arc length, because you're going to get some really messy integrals, because you're going to end up with square roots. And integrating square roots, hard if you don't have anything outside the square root, so you cannot use them. So we will really thrive at getting perfect squares under those radicals. So you can take the square root of the perfect squares, and then you integrate a friendly function, okay? So I have to be careful with my example, so I cannot just make them up.
Do you want the number 1 plus squared to be a perfect square?
Yeah, so the radicand has to come out to be a perfect square in order for you to square root it and then have a nice integral. So you'll see, I mean, we'll do it in steps. We'll be like, okay, take the derivative first, then square the derivative, add 1 to it, and then stare at it, notice a perfect square, and then factor, and then take the square root type of deal, okay? Yeah, but again, you complete the square, but then when you complete the square, you add subtract at the same time. Right. So you're going to have a perfect square plus or minus something else still under the radical. So we'll try to make it not as bad algebraically. So the functions will look completely ridiculous at first. When I'm going to write a function, here's an example. Find the length of the curve. Find the length of the curve. Y equals x squared over 2 minus natural log of x over 4 between 2 and 4. I won't even bother sketching this thing. Who cares? It's not that important in this case. Well, in some cases it is important if there is some symmetry. Okay, but this is some messy thing. So just again, remember the arc length is, the integral in this case will be from 2 to 4 square root of 1 plus y prime squared dx. Okay? So we'll take steps. First step is to take the derivative. Just find the y prime. Okay, so we're going to take it slowly. So y prime, what is that going to equal to? X minus 1 over 4x. Right? Straight up derivative. So that's nice. That's friendly. Second step, we need to figure out what the square of that derivative is. So the second step, we have to figure out y prime squared. So we have to square x minus 1 over 4x. So that's algebra. We're going to square a difference. So that's x squared minus 2 times x times 1 over 4x plus 1 over 4x squared. Right? Using our favorite formula, this whole shebang reduces x and x, 2 and a 4. So this is x squared minus 1 half plus 1 over 4x. I'm just going to leave it like that as a big square. So x squared minus a half, that's a plus 1 over 4x quantity squared. Is that okay? Keep this in mind. Keep this form in mind. So x squared minus a half plus the other thing squared, right? That came from this. That used to be a perfect square at some point, right? So we got that. Now, so we're over here now. The next step would be to add 1. So let's do this. So we're going to have the third step. I don't want, okay. 1 plus y prime squared. So it is 1 plus whatever that thing was. So that's x squared minus a half plus 1 over 4x squared. Right? And then, so you have a half minus a half, that's a half. So I'm going to write it in this fashion, x squared plus 1 half plus 1 over 4x squared, which is a perfect square. Right? Because again, think about this. The previous step, we had x squared minus a half plus 1 4x. This is why I left it in this form. The only difference is negative 1 half became positive 1 half, right? So therefore, if previous one was the perfect square with a minus, therefore this one is a perfect square with a plus. So this is, by using the same formula, gives you x plus 1 over 4x quantity squared. So this is basically, it's one of those classical situations where we claim that the calculus is a joke. You just took a derivative, right? It's all you did from calculus. The rest is just algebra. You're squaring, subtracting, factoring. Haven't done any calculus since. And we're going to get a nice little integral, so calculus, again, going to be easy with the nightmarish algebra in between, right? Because then when we put it all under the square root, I can actually start computing the integral at this point. Because we are, so S is integral from 2 to 4, and then just the square root of x plus 1/4 x quantity squared dx. Square and the square root go away, and you end up with a very, now actually it's 1 over 4x. We get an integral from 2 to 4 x plus 1 over 4x dx. Right? All right, well, I think we can integrate that, can we? What would that equal to? Now that's a natural log thingy, right? Minus a quarter of natural log, right? Because you just think it's 1/4 times 1 over x. So it's plus 1/4 ln of x. You just, you don't need to think of this as 1 over 4x. It's just constant times a function, integrate a function, you get natural log from 2 to 4, right? So let's see. So you plug in 4 squared over 2 plus 1/4 times ln of 4 minus 2 squared over 2 minus 1/4 ln of 2. Is that okay? So again, it's some kind of a numerical expression. I'm sure we can compute this. So what do we get? What do we get out of this one? 8. And what do we get out of that one? 2 and 8 minus 2, 6, right? And then plus, I can factor the quarter out. And then we have natural log of 4 minus natural log of 2. So the difference of logs becomes a division. So it's 4 over 2. So it's 2, right? So it's minus, plus ln of 2, right? So whatever that is. So ln of 2 came from ln of 4 minus 2, because you replace. So whatever that thing numerically will be the length of that curve. So again, calculus was not bad. The algebra was a little iffy, right? Questions? You can, of course, plug that thing in your calculator to get the idea. Oh, yeah. Yeah, I'll take that. I'd rather you write it like that. I don't want to see because that means I'll have to take a calculator and then check that. But yeah, this is the exact answer. All right, so find the length of x to the power 2/3 plus y to the power 2/3 equals 1. Ooh. Okay. Now, clearly, not a function, right? It has this circular smell to it. It has the same kind of a setup. You have a x squared, right? It's a cube root of x squared, and then cube root of y squared plus, and then equals 1. So there's definitely some kind of a thing that's symmetric around the x-axis, symmetric around the y-axis. It's symmetric around the origin, because it doesn't matter whether x is positive or negative, everything comes out. So it's kind of like a circle. So you have a thingy that hugs the origin, and that's symmetric around the origin, it's symmetric around the x-axis, symmetric around the y-axis, right? So in each quadrant, it has the same exact image. That's what I'm trying to say. Because it's hard for me to compute the arc length of something that's not a function. But if I can say, well, if I just compute the arc length in at least one of the quadrants, then I'll just times it by 4, and then it will be easier for me, right? So if I just solve for y in terms of x, there will be a function, and just take it in the first quadrant, right? How does that sound?
So just by solving for y, you reduce the impact.
Well, I'll just reduce it. Well, think about the circle. In the circle, if you solve for y, you'll get plus or minus the square root. So plus, that's the upper semicircle, minus is the lower semicircle. So when I solve for y, I'll get an upper whatever, and then the lower whatever. Okay? But then the upper whatever is also symmetric with respect to the y-axis. So I can just take it from 0 to whatever the x is, which in this case is just kind of like a unit circle. It'll be like from 0 to 1, because that will be the radius version of whatever that thing is, right? So I mean, I'm even doing this without sketching, okay? Because we can analyze this without seeing the graph, because it'll be hard to graph. We haven't graphed things like that. And of course, if we solve for y, you get y to the power 2/3 equals 1 minus x to the power 2/3, right? And then to get y by itself, you have to cube everything and then take the square root. So when you take the square root, that introduces plus or minus. So it's 1 minus x to the power 2/3 quantity cubed, like that.
So it's just 1 over minus x.
Well, no. I mean, you're cubing the whole difference, so that's a big mess, right? But we'll see. Maybe something good will happen. It should. Remember, there's problems with the arc length. I'm looking at a solution. The problems with the arc length, they start messy. I mean, the functions look ugly, but eventually you get pretty integrals, because otherwise you're done. Just for fun, we can graph just one of those positive square roots. If I go here, so if I just graph in square root of, what was it? I need a double thing, right? It's 1 minus x to the power 2/3, right? And then that cubed, and then close the square root. Is that close enough? Okay, so I only got, it didn't even give me the other part. Why didn't it give me negative? No negative? Why not negative? And I cannot move it? Well, anyways, it should have given me 2. There's no reason for not to use negative numbers on that one, right? Because of the 2. X becomes, do you recognize this? It shouldn't be, we should be able to plug in negative values for x because it gets squared anyways, right? So it'll do this on both ends. So yeah, foo plot is a little, sometimes it gets a little weird graphs, but at least it gave us 1 quadrant that we're after. That's good. But the graph of this thing will be, it's kind of like that, like a fancy little, what is it, like a diamond with the curves, right? So the whole top part is the positive square root, and the bottom part is the negative square root. But we'll be after just this thing. Okay? So we'll set up an integral from 0 to 1. We'll have to take a derivative of that, and then we'll have to square that derivative, and then add 1 to it, and then hopefully it comes out to be a perfect square, so you can take a square root of it again, right? Because the formula is messy. Because keep in mind, the formula is, in this case, it's from 0 to 1, and it's a square root of 1 plus the derivative of that squared dx. And by that, I mean all of it just taking a plus. Just taking a plus version. We need one of them. What? Times 4. Very good. Thank you. Times 4. Because we have 4 pieces. Right? So here calculus might get a little sneaky, but we can, just taking a derivative. So first step is to take y prime. So that's, how can I write it? I can write it like this. It's 1 minus x to the power 2/3. Everything raised, it's a cube root, it's a cubic and a square root, so everything raised to the power 3/2. Is that okay? So that's the same function. So square root and then a cube, it's a power 3/2. So we're taking a derivative of that. So we're going to use the chain rule, right? 3/2 comes down. Then it's 1 minus x to the power 2/3. Now subtract 1, right? So it gives me just 1/2. And then times the derivative of the inside function, which in this case is negative 2/3 x to the negative 1/3. Is that okay? So 3/2 will cancel with 2/3, so those two cancel. So we'll end up with negative x to the negative 1/3 times 1 minus x to the 2/3 to the 1/2. So that's the derivative. Calc 1 style, right? Yeah, you'll get, you have to use the expansion of, which we haven't done yet, by the way. We'll learn how to take a square root of a sum or difference in this class. It's infinite. So we cannot distribute the powers. But anyways, but the good news is that thing gets squared, so that will take care of that 1/2 power, right? Because remember, it's a 1 plus derivative squared. So when we compute y prime squared, we get negative x to the negative 1/3 so negative 1/3 times 1 minus x to the 2/3 to the power 1/2, everything squared. So the square will kill the negative in front, we'll make it x to the power negative 2/3, right? You're squaring a 1/3, you get a 2/3. I mean the power, you multiply exponents, times the square will kill the 1/2, so it's 1 minus x to the 2/3, period. Right? When you're just squaring that. Well, yeah, you can square a product. So right, it's a product, so I square each part of the product. I'm not allowed to square sums like that, but products, sure. So see, with no more power there. So now I can distribute this. So this will give me x to the negative 2/3 minus, what is x to the negative 2/3 times x to the positive 2/3? 1, right? They cancel each other. So minus 1. And we're about to add 1 to that. So once we'll cancel, we'll end up with x to the negative. Now it doesn't matter whether it's a perfect square. You just have a x expression under the square root, but it is actually a perfect square anyways. So things are about to work out in a friendly fashion. Because remember, it's 1 plus the prime squared. So we already computed the prime. So we get 1 plus x to the negative 2/3 minus 1. So the 1's go away. So x to the negative 2/3. So this is now my radicand. And I can take, again, it's a perfect square, but now it doesn't have to be, right? Because you can always write it as any way you like it with a square root. So now it's a computable integral, if there is such a thing. So finally, s would be 4 times the integral from 0 to 1, the square root of whatever that is. What? Adam, what? No, you divide now, so it becomes 1/3, right? Because you're raising 2/3 to the power 1/2. So 2's will cancel. So you'll end up with the x to the negative 1/3. So it's a 4 times integral from 0 to 1, x to the negative 1/3 dx. So that's a very nice integral. So again, algebraically, it's a mess. But again, so these functions, they start ugly, but so they're very carefully chosen. So you're actually able to compute it, because there are some ugly integrals here. So anyway, so the rest is calc 1-ish. So you add 1, it becomes x to the power 2/3, and then you multiply by the reciprocal, so it's 3/2 evaluated from 0 to 1, right? So 4 times 3/2 is 6. You plug in 1, it's 1. You plug in 0, it's 0. So it's just simply 6. So that's the length of that shape.
like the outer curve of the arc length?
Yeah, so that's, if you're just going to walk along the path, that's how far you're going to walk, 6, whatever units, right? Let's do, this is a Calc 1 thingy. I'm sure you did this in Calc 1. So length of, yeah. So I want to do length of a hanging wire or a cable. You did that in Calc 1. You have like 2 telephone posts and a thing hanging, and use the hyperbolic functions to model that, right? And those are, what? That's all right. So it's some kind of a cosh type of problem. So we'll just set it up and we'll be able to figure it out. Can I go to the next page? Yeah, okay. So length of a hanging wire. So let's say we have 2 poles, and then there's a wire hanging. So basically the way we do these problems, it's beneficiary to put them on the x-axis kind of with a symmetry. And we're just going to label that. We're going to call this point B, that point negative B, and this point is A, the height at the lowest stage. So then the actual formula for this curve, just the wire, is y equals A times cosh x over A, for whatever reasons that we don't need to know. Okay? So I want to find the length of this thing, okay, in general. So again, by the symmetry, we're just going to do length of half of that, and we're just going to double it, so we'll integrate from 0 to b, instead of going from negative b to b. And we'll set it up using the arc length formula. So for now, the length will be 2 times the integral from 0 to b, the square root of 1 plus y prime squared dx, just like before. So now we just have to go through the motions and find all the fun stuff. Actually, it won't be that bad if you remember the derivative of cos, sinh, or that's what he calls it. But anyways, right? So it's almost like trig. Here, derivative of one is the other. There's no minus. So y prime would be a times 1 over a, and then, well, sinh of x over a, right? By the chain rule, 1 over a comes out as the derivative of x over a. So a's cancel. We'll get this. Not over 2, over a. I don't know why I wrote 2, for no reason. A is just a general constant. Could be 2, but we're doing a general thing, right? Well, I'm going to kind of skip a step, because in this case, it's not that hard. I'm just going to write 1 plus y prime squared, because, I mean, y prime squared is kind of easy in this case. So we'll get 1 plus sinh squared x over a, right? So that's the radicand. And I already see Aaron is checking his hyperbolic function identities, and he's about to tell me that 1 plus square of hyperbolic sine is?
Isn't it like cosh squared? Some weird hyperbolic.
Which one is that?
Like cosh squared plus sin squared equals 1.
No, there's a minus. Yeah, minus. Which one is that? Is that sine minus cosine? Or? Well, you look. I mean, I can look up too. Yeah, it's cosine. Yeah, I just looked it up. Yeah, so it's a hyperbolic cosine. So here's a fundamental hyperbolic identity. Cosh squared x minus sin squared x is 1. So therefore, cosh squared is 1 plus hyperbolic sine squared. So we're in big luck by the hyperbolic identity. This is in fact a perfect square, because we again like to have perfect squares inside the square root, so we can easily take the square root and then follow with integration, right? So therefore we can actually do this thing. The actual length would be 2 times the integral from 0 to b square root of cosh squared of x over 2 dx. The square root and the square is going to agree.
Is it over A or over 2?
Over a. Why am I keep putting over 2 again? This is, I don't know why. No, I have no idea. No reason for me to put 2. I'm going to, oops. No, I don't know why. Thank you, and thank you again. So 2 times from 0 to b, just cosh x over 2. What? I'm done. Here we go. Maybe it's a color of the pen. I don't know why. No? I usually can find the reason for the silliness, but not this time. So then, what is the integral? Integral of cosh. Yeah. Now, how do you fix the whole x over a business? What are you missing? An a. We need another a, right? Because now it's an integral. So 1 over a comes out. It has to kill the a in front. And you integrate this from 0 to b, right? Evaluate it from 0 to b. Now you plug in b, you're going to get a b. So it's 2a sinh of b over a. And you plug in 0, right? You get 0. So that's it. This will be the length of that hanging wire. Now, if I give you the values for A and B, if I tell you, let's say, the lowest point was, let's say, 10 feet, and they were 100 feet apart, right? So the A is 10 and the B is 50 because it's halfway, right? So if we're actually going to do this one, so this is 10 and this is 100, I can actually find the length will be 2 times 10 and then hyperbolic sine of b is 50. Again, it's a halfway over 10, so this is 20 hyperbolic sines of 5, right? Now you can either use a calculator to compute a hyperbolic sine, or you can use a definition of a hyperbolic sine, which is, what is a hyperbolic sine? That's right. So it's e to the x minus e to the negative x over 2. And you take the derivative, you get e to the x plus e to the negative x over 2, right? So these are your, so whatever that equals to, right? That equals to a number.
And so is that the one for any piece of painting?
Yeah. Yeah, well, there are some other factors involved, but if you just if you just imagine putting the set of x's like that, then the result it is. All right, so, okay, we have a little bit of time left. The other thing we can do, maybe I can verbalize it. I don't know if I have time to derive it, but so we've been taking a curve, right? And we've been rotating curves. We can find the volume. Well, I can rotate a curve and find the surface area of that object as well, right? That's a fun thing to do. But we're actually going to do it a little differently than we did everything before. Now, how did we do everything before? So when we're trying to find something that we don't know how to find, we would solve little pieces and then just find the simple either areas or volumes and then add them all up, right? Now here we're going to do it a little differently. Again, I don't think I'll derive a formula because I'll get all psychotic with geometry again. It's a geometrical nightmare, but I think I'll. So let's say if I rotate this thing, let's say around the x-axis, so I get like, I don't know what that is. But, so then I'll just take a little strips, right? I'm just going to cut this, let's say this little piece, right? And I can find its area, right? So it's an area of a, what do we call that thing last time? It's a pyramid, the frustrum, only circular frustrum, right? What? Yeah, kind of a part of a cone. Yeah, so it's no longer a pyramid. But the thing is, I mean, we can technically just say, oh, what the heck, it's just going to be, you know, whatever the length, the delta x or delta y is, times the circumference, right? Or, just for the benefit of getting a highly acute result, we're just going to create a mess mathematically. This is going to blow your mind. So check this out. I'm going to say, well, who cares? It's a curve. Curve is a straight line, okay? And then I'm going to say, well, who cares? Straight line is a slanted line. So I'm actually going to approximate the length of a straight line that just simply dy by the literal arc length of that curve. And I'm going back to the curve. Does that make sense? So I'm saying that, you know, it's approximately the length of whatever that curve is. So I'm going to try to set up this integral with respect to the arc length of the little piece.
So you're like folding in the thing that we just did into another integral?
Yeah. So in the end, again, I'm not going to do through derivations. I don't have time. But I'll end up with the integral. I'll definitely going to have a 2 pi somewhere because there's a circumference floating around. And then I'll have something in here that I will fill in eventually. But in the end, I'm just giving you a preview. It will have this setup. It'll actually have 1 plus the derivative of the function squared dx. It'll have this ending here. Okay? And this is precisely the integrand from the arc length, right? So therefore, this portion right here is the differential of, it's a ds. If s is the integral of that, then ds is that dx. So we'll be able to set up the surface area of revolution, and this is a preview. I'll kind of summarize it all later, with something here, we'll fill in the blank, and then ds. So we'll actually have this new parameter. It's not with respect to x, it's not with respect to y, but it's with respect to the arc length. The cool thing about the arc length, it's irrelevant whether you're doing the arc length with respect to x or respect to y, you're getting the same arc length. So we'll actually have, like before we had problems that it's easy to set up with respect to x, but hard to set up with respect to y. Here we won't care. We'll be able to almost set them all up with respect to the arc length, and then our integrals will simplify them dramatically, which you might not appreciate in this class, but in Calc 2, you will have this. I'm sorry, in Calc 3, you are in Calc 2. In Calc 3, you will probably going to have a little, how many of you have been through Calc 3? Just one? Okay. So you're going to do this kind of a weird reparameterization of your integrals. Instead of just integrating with respect to your normal axis, you just integrate with respect to some other notion. So this whole fakish, we kind of want that because it'll be better off. All right, I'm not going to derive it now because it's going to be crazy. But yeah, I have your homework 1 kind of graded. You did good on it.